Hello everyone, I am one of your instructors for ENS181 Engineering Mathematics, Carl Martin A. Aldueso. So our first topic is about Introduction to Differential Equations. So the words differential and equations certainly suggest solving some kind of equation that contains derivatives such as y prime, y double prime, and so on. In this subject, one of the tasks will be to solve differential equations such as, for example, y double prime plus 2y prime plus y equals to 0 for an unknown function of y. In order for us to read and study differential equations, we need to know some terminologies. So we examine the link between differential equations or DEs and the real world. So practical questions such as how fast does a disease spread, so involves rates of change or derivatives. So the mathematical model of phenomena, experiments, observations, or theories may be differential equations. Later on in the topic, we will know the use of differential equations or how our real-world problems can be described by differential equations. So an equation containing the derivatives of one or more unknown functions, or called the independent variables, with respect to one or more independent variables, is said to be a differential equation. So looking at this equation, our dependent variable here is our x. The independent variable is t, which means the value of x depends upon the value of t. We classify differential equations according to type, order, and linearity. So first, let's talk about notations in writing differential equations. We have Leibniz notation. So we have dy over dx. For the second derivative, we have d squared y over dx squared. We have the third derivative, so on and so forth. So the Leibniz notation clearly displays both the independent and dependent variables. So in this case, our dependent variable is y. Our independent variable is x. So we can also write our differential equations using the prime notation. So we have y prime, y double prime, y triple prime. So y as the independent variable. So this notation, it is more compact when writing equations such as, for example, we have y prime plus 5y equals to e to the x. So the fourth derivative is written as y to the 4 with parentheses instead of y with 4 primes. So by type, we have different types of differential equations. The first, if a differential equation only contains ordinary derivatives of one or more unknown functions with respect to a single independent variable, it is said to be an ordinary differential equation. So for this equation, we have one dependent variable and one independent variable. This equation, we also have one dependent variable and one independent variable. Now for this equation, we have now two dependent variables. We have x and y, and then one dependent variable, which is t. Now for the next type, an equation involving partial derivatives of one or more unknown functions of two or more independent variables is called partial differential equations, or PDE. So now, this case, instead of a single independent variable, there are two or more independent variables. So looking at this equation, we have independent variables x and y. We have independent variables x and t. Then independent variables y and x. So classification by order. So the order of differential equation, the order of the highest derivative in the equation. So the following equation is the second order derivative. The order of the differential equation is the order of the highest derivative. So looking at this equation, this is a second order ODE because the highest derivative is the second derivative. So first order ODEs are occasionally written in differential form, such as this form. So for example, if y denotes the dependent variable in, for example, y minus x, quantity y minus x dx plus 4x dy equals to 0. Dividing the equation by dx, we get the alternative form. So using the prime notation, where y prime is equal to dy over dx. Looking at this equation, we have y minus x dx plus 4x dx dy equal to 0. Dividing the equation by dx, we have y minus x plus 4x y prime equal to 0. Or we have 4x y prime plus y equal to x, which is this equation. So in symbols, we can express an nth order ODE in one dependent variable by the general form. We have this general form where f is a real valued function of n plus 2 variables x, y prime up to y to the nth derivative. So classification by linearity. So the nth order ODE, this form, said to be linear if f is linear in y prime up to the nth derivative. So this means that an nth order ODE is linear when, so we have an of x times y to the nth derivative plus an minus 1 of x times y to the nth minus 1 derivative plus dot 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 a1 of x y prime plus a naught of x y minus g of x is equal to 0. This form is equal to 0, or can transpose g of x to the other side. We have this form. So there are two special cases for the first order and the second order. We have the first order, this form, and we have the second order, this form. So the dependent variable y and all its derivatives, y prime, y double prime, have the first degree. That is, the power of each term involving y is 1. The ODE is also linear if the coefficients a0, a1 up to an depend at most on the independent variable x. So examples of linear ODEs, we have this equation, an example of a linear differential equation. This equation is a linear differential equation, and this equation is an example of a linear differential equation. On the other hand, a nonlinear differential equation is simply one that is not linear. So this means that the function involves nonlinear functions. Looking at this equation, this coefficient depends on y. So remember, our coefficient must depend on the independent variable x. For this equation, we have a non-linear function. So we have a sine function. Then for this function, we have y that is not a power of, that's not a power of 1. We have y squared. So y squared is not a linear function. Now let's talk about a solution of an ODE. So any function defined on an interval I and possessing at least n derivatives that are continuous on I, which when substituted into an nth order ordinary differential equation reduces the equation to an identity. So that function is said to be a solution of the equation on that interval. So for example, this function is the solution of this differential equation on the interval negative infinity up to infinity. So first, let's get the first derivative of this function with respect to x. So dy over dx is just e to the 0.1 x squared. Then we have the derivative of this exponent. We have 0.1 times x times 2. So we have dy over dx is equal to 0.2 x e to the 0.1 x squared. So now if we substitute this equation to the left hand side of this equation, we have 0.2 x e to the 0.1 x squared is equal to 0.2 xy. So remember, our y is just e to the 0.1 x squared. We have 0.2 x e to the 0.1 x squared is equal to 0.2 x. Substituting the value of y of e to the 0.1 x squared. Indeed, this equation is a solution of this differential equation on the interval negative infinity to infinity. There are also two kinds of solutions. So we have explicit and implicit solutions. So a solution in which the dependent variable is expressed solely in terms of the independent variable and constants is said to be an explicit solution. So for example, these equations are expressed solely in terms of the independent variable. So looking at the first equation, we have the dependent variable y is equal to 1 over 16 x to the 4th. So y is expressed solely in terms of x. The same with the second equation and third equation. So this means that these equations are explicit solutions to a certain differential equation. On the other hand, a relation g of x and y is equal to 0 is said to be an implicit solution of an ordinary differential equation on an interval I, provided that there exists at least one function that satisfies the relation as well as the differential equation on that interval. So for example, the relation x squared plus y squared equal to 25 is an implicit solution of the differential equation dy dx is equal to negative x over y in an open interval of negative 5 and 5. By differentiating this function, we get 2x plus 2y dy or dx equal to 0. So if you solve for dy over dx, dy over dx is just equal to negative x over